So this video is the rest of chapter one, sampling, error, and bias, and variables, and just a bunch of fancy words for saying more vocabulary. Yay! So looking at this, going to cover 1.1 and 1.2. No. 1.2a and 1.2b. There we go. Okay, so here is 1.2a, sampling, errors, and bias. And just remember, every time you see that red heading, it's a separate assignment in Newton Alta. And this really only affects like this first week or two because the sections are so short and just vocab that I just kind of pushed them all together in the videos. But I did separate the assignment so you can get those separate 100% completions because everybody loves the fireworks. Have you tried the Newton Alta yet? There's little confetti fireworks at the end. Okay, focus. Here we go. Sampling, non-sampling errors, and bias. So, and these kind of get a little tricky. So again, you always want to have your vocab out, like this page out when you're doing homework, quizzes, and the test, just to be able to differentiate between each vocab word. So a sampling error is an error caused by the actual process of sampling that varies from sample to sample because the sample is not the whole population. So we talked in the last video how the sample is something that we choose that represents the whole population, but we typically don't interview or survey the literal entire population, especially when we're talking about something like the population of the United States. If all you're talking about is the population is your immediate family or your classroom or something like that, that's manageable. You would look at the whole population, but typically we look at a sample. And because the sample will never be literally the whole population, unless, of course, that's not what I meant. It'll never be the whole population, no matter how well you plan your sample, it'll never literally equal the population. So just errors naturally occur, and that's called a sampling error. A non-sampling error is errors caused by factors not related to the sampling process. So those are other types of errors. For example, like bias. So bias is when your opinion will influence the results. We'll do it. All of these we'll do examples of in just a second. And then sampling bias is kind of ties back to the last video where I said your sample needs to be representative of the population. So if it says if the sample, oh, that's almost wrote on my screen with my ballpoint pen. Okay. Where the sample is collected from a population, but some members are not as likely to be chosen, then that's sampling bias. That means your sampling method is wrong. So for example, I talked about convenience sampling in the last video. That would lead to sampling bias because in that example, you're just standing outside of a grocery store and interviewing those people that come to you, or standing in the middle of the quad or something like that. So that would be sampling bias. Okay, so which of the following contains a sampling error? So the first one that says, a study is conducted to determine the favorite subject of all the students in your high school. Students in your homeroom class were used as a sample. All right, so this is not sampling error because the problem is that the sample, which is our homeroom class, is not representative of the whole high school. Now, how's a homeroom class chosen? Do you even have a homeroom class? Are you even in high school? Does it even mean anything to you? Let's just talk about different ways to view homeroom class. I never had one, so I've seen it on TV. Does that count? Some homeroom classes are just like a zero period type of thing where it's just basically everyone in your first period, but they have that extra time for announcements. Okay. Other people's homeroom class are a separate class where the teacher checks in. And it's made up from people all throughout the school. Other schools, the homeroom class could be grouped by like all the athletes in one class and all the drama, I don't know, just different types of grouping. So since it doesn't say how this is grouped, we have no reason to believe that it represents all students in the high school. It's probably just a bunch of freshmen in one class, a bunch of sophomores in another class, and so on. And that would not represent the whole high school. So that is bad, but it's not a sampling error. We're looking specifically for a sampling error. And that is where there's an error due to the fact that the sample is not the whole population. Okay, next, a study is conducted about where the best travel destinations are, either Europe or Asia. People who live in big cities throughout Europe are used as a sample. Okay, so from what they said, I mean, they didn't really say how they chose them, so we'll just give them the benefit of the doubt that they chose them using a valid method. And they're asking people throughout Europe in the big cities, and it seems reasonable. I don't see any obvious like red flags in this one, but we're not asking everyone in Europe. We're only asking people who live in big cities. We're not even asking everyone who lives in big cities. So this right here is not the population of Europe. It's a sample, but it's not the whole, well, even at a whole. It's not the whole population of Europe. So issues could arise. It says, I'm trying to read what the definition, that an error is caused by the actual process. Errors could arise even if you choose a very representative sample of people who live in big cities. You're not asking every single person who lives in a big city, and you're certainly not asking every single person who lives in Europe. So this is a sampling error. There's no glaring mistakes, but it's just things could happen because you're not asking everybody. And that's kind of an error that we learn to live with. We accept that error because we aren't going to be asking literally everybody. So we just acknowledge that there's an error and we move on. And the error is called sampling error. All right. That is one. Let's just go through the other two just to see. You're going to notice on your homework, sometimes it says select the one answer, and other times it'll say select all that apply. And so we're just going to keep reading just to see if there's any more in here. So the first one was not, the second one was. The third one, a hospital conducts a study about a new heart monitoring software. All patients who use the software were used as the sample. Okay, everybody was asked. Everybody in this whole place was asked, therefore, there's no error. The sampling error means you didn't ask everybody. So you could even say that for number one. You could say, because remember how I was, do you remember? It was like 2 minutes ago. Remember how I was saying that the homeroom class may or may not be representative of the high school? Like, forget that. Let's say it was representative. Who cares? This question is asking, did you ask the whole population? We did not. We asked the homeroom class where the whole population was the entire high school. So, okay. It's kind of early when I'm making this video, so sometimes I forget my point. So let's just go on to the last one. The last one says a study is conducted by a cereal manufacturer about 2 brands of cereal. And a question on the survey reads, do you prefer the delicious taste of brand X or the taste of brand Y? Okay, there's some bias going on in there. Remember, bias, this third one down, is talking about an individual's opinion or preference. And here we have the word delicious, which is a preference. So this is a problem, but it's not the problem that we were asking about. So that's not a sampling error. It's just a problem called bias. Yay, vocabulary. Okay. Again, lots of vocab in chapter 1. Keep these definitions handy as you work through the homework, quizzes, and test. Next up, we have some, and these aren't really questions, it's just kind of information we'll just run through. I'm not going to read everything, so feel free to flag this and read it again later. But it says, we're talking about a misleading statistic. So problems here would be bias, error present when data is collected from samples that are not representative of the entire population. That could lead to a misleading statistics, or an outlier, which is a data point that is far away from all other data points. And for right now, that's going to be our working definition of outlier. Although by the end of chapter 2, we'll have an actual formula for that. But right now, an outlier is just something that stands out. So for example, if you were watching The Bachelor and they have all the girls on there and they're like 20s, 25, whatever, however old they are, and then you have like a 60-year-old as a contestant, that would be an outlier because her age is considerably distant from the other people's ages. So what that distance is that determines that. Again, we will have a formula later, but right now an outlier is just something that's far away. Outliers happen. Where could an outlier happen? In earthquakes. You could have a city that has a bunch of small earthquakes, and then one day they have a really big earthquake, and then they go back to having really small earthquakes again. That's an outlier. It just happens, but it could skew things like the average. We'll get into all of this later. Just things that could lead to misleading statistics. But bias is definitely one because it's when the sample is not representative of the entire population. So the first category, we have the data is misleading because the sample is biased. So some things that happen here, it says samples are too small, or maybe, oops, what am I doing here? I'm highlighting this. No, I just made a rectangle and went away. Okay, samples are too small or insufficient. Those might be unreliable. And I want you to not make any judgments about the word small. Everybody's example of what is too small or what is too big or what is a lot, those are kind of vague words because it really depends on what you're talking about. For example, if I had a lot of pennies in my pocket right now, I probably would have like 50 or 60 pennies. That's a lot of pennies in my pocket. But if I had a lot of spiders on my face right now, that would probably be like 1 or 2. Like 1 or 2 is a lot of spiders to be crawling on my face, but 1 or 2 is not a lot of pennies to have in my pocket. So a lot, too big, too small, those words, they don't really mean anything because the value of them changes depending on what you're talking about. So we'll talk about sample size a little bit later, but if it's too small, it could be unreliable. Self-selected samples are often unreliable. For example, who wants to complete this survey? Well, you chose to complete the survey, therefore you're self-selected. It's not necessarily a representative of the population. A good example of this would be like American Idol or Dancing with the Stars or anything where people at home choose to vote. That's self-selected. Bias can be present in the phrasing of the questions. We just did that before. Do you prefer the delicious taste of this or that? So that can also lead to bias. Okay, what about outliers? So if the data is misleading because it contains an outlier, here's an example. The restaurant says the average price is $7, but here's their menu: $1, $9, $8.50, and $10. So technically, if you calculated it, the average is $7, around $7, but 3 out of the 4 items cost more than $7. Why is this? Because one of them costs $1. So that's not very representative of the data, and it's misleading. So if you have ever scrolled through social media and you've seen an ad and it'll be like $5 shoes, and then you click on it and it's like size 4. That's why they're $5. Those are misleading statistics because they're using that one really low value to make it seem like everything is inexpensive, just like this menu here. They're taking advantage of the fact that that $1 lowers the average, which makes it sound cheaper than it is. Okay, almost done with this section. We have the data is misleading because the statistics are displayed improperly. So you'll notice both of these bar graphs, they say A and B, and then on the left-hand side, A is at 120 on both of these graphs. So they're both at, what did I just do? There we go. They're both at 120, and then B is both at 150, but the distance between 120 and 150 is very different. And then also, typically, because this is how our eyes are trained from algebra, we think of this bottom here as 0. And if this bottom is 0, compared to the 120, that distance 120 to 150, that bottom being 0 makes sense. But here, if we said the bottom was 0, this distance being 120, and then that big fat distance being 30, doesn't make sense. So this is misleading because it's being the second one's being super dramatic. Like if I was looking at this, I'd be like, oh my gosh, there's so many people in B. I have to choose B to be like everybody else. But really, there's only 30 more people that chose it. There's still 120 people that chose A, or whatever this is talking about. So the scale, because there's no scale, it's misleading. Okay, finally, and this is actually incorporated into what I just said, a truncated bar graph. I keep moving my mouse like I can highlight something. Okay, a truncated bar graph where it does not start at 0, and that's exactly what happened above. So that's the same as that, the one with the picture. Okay, yay, more vocab. Don't worry, plenty more vocab in the rest of this video. So again, red headline, red heading, new section of the Newton Alta homework. Probably is only going to happen through chapter 2, and then I'll do one section per video after that. Okay, variables and data of measure. We talked about experimental versus observational experiments. Not experimental, the cause and effects. So we have this is more detailed about the cause and effects. The last video we did, I was talking about the guy that was doing the science experiment, and like these seeds went in at 20 degrees Celsius and these seeds went in at 50 degrees Celsius. Well, what we have there is we have an explanatory variable and a response variable. So the explanatory variable is what the person doing the experiment controls. The response variable is the response given back. So in the previous example, if you just flip back, hopefully you have a notebook going, just look back to that last, oh, you know what? I have a notebook going. I forgot I'm using OneNote this semester. Okay, 1-1. Oh my gosh, I'm a genius. Okay, this is exactly what I was talking about right here. We have this experiment versus observational. We said this was an experiment, and it talked about the controlled factor, which was the temp. That's what this biology student controlled. And then the response was how the seeds grew. I think it was the germination time. So the time it took them to grow. So going back to this one, oh, I kept my space. This is very exciting. Okay, the explanatory variable is what you control. So it's the temperatures for each group of seeds. And the response is how whatever you're experimenting on responds to that. And so for this example, the response would be not the height of the plant, the germination time, how long it took the plant to germinate. I'm not a scientist, don't judge me. How long it took it to like pop out of the soil or whatever. Okay, so explanatory variable is what you control as the scientist or as the surveyor, and the response variable is how they respond. Another way to think about this, if you're algebra brained, the explanatory variable is the X, it's the input. And then the response variable is the Y, it's the output, the survey response, the growing of the plants, the whatever we're doing. So here, we want to know if there's a relationship. I didn't mark this example as a number, but here we are. Is there a relationship between the amount of time a student spends studying for an exam compared to their grade? Identify the explanatory and the response. So in this case, we have a student. What can the student control? The student can control the amount of time spent studying. So that's going to be the explanatory variable, because that's what they can control. And by controlling that, they then take the test, and whatever the grade they get on the test, that will be the response variable. This is how studying works. You put in the time to study. Ooh, this is a great PSA for do your homework, study for this class. You put in your time to study, and then that will directly affect how well you do on the test. It's not the other way around. The other way around would be me saying, okay, I am going to get a B on this test, and therefore I just study the amount of time it takes to get a B. That doesn't make sense. That's not how we work. We work on, I'm going to try my best. I'm going to study for 3 hours a day, and that translates into what my grade is. Or maybe, you know what? I don't really care about this class. I'm going to study 5 minutes total, and then that will translate to the grade on the test. That's how it works. So the explanatory is how much time you spend studying, and the response is the grade on the test. Okay, not quite the same example, but there is another vocab word in here. It's a lurking variable. And so a lurking variable, we don't really have a definition of this written down, so I'm just going to say it. A lurking variable is some other reason that happened. So let's go back to the test real quick, because I gave an example of like, oh, somebody studied 5 minutes on the test, and somebody out there in YouTube land right now is like, that's me. I studied for 5 minutes and I get an A on a test. Why? Not because they studied for 5 minutes, because of other reasons. They love the subject and have been ingesting all that information their whole life because they just can't get enough of it. Or, you know, that one kid that's like super duper smart, no matter what, they just always get A's on everything. It's not because of the time they studied on the test in certain situations. It's just because that's how their brain is wired and they just get it. They just need to see it that one time and they get it. So those would be lurking variables when there's something else besides the explanatory variable that's contributing to the response. So here we have a manager who wants to know if cold brew coffee, which is higher caffeine, has an effect on the worker's production before lunchtime. So for 5 days, the manager brews cold brew, okay? And then they work. And the next 5 days, he just has regular hot coffee, which is hot and then less, just regular concentrated, I guess, regular amount of caffeine. The manager found that when cold brew is brewed, there is more production at the plant before lunchtime. Okay, so you would think, okay, manager saw cold brew leads to more production. It must be the cold brew. And this question is saying, give 3 examples of lurking variables. So I'm going to give 2, and then I'm going to give you a chance to come up with a third one, because I want you to kind of just have fun with this, and we could be serious or we could be silly. So serious could be the temperature. The temperature could be affecting this, because when it's hot outside, think summer in the Central Valley, what are you drinking? Do you want to sit there and drink a hot coffee, or do you want to drink a cold coffee? In which case, maybe people are only drinking cold brew coffee. And on the other 5 days, when the hot coffee is offered, they're not drinking any coffee. So it might not be the fact that it's cold brew. It might just be coffee in general, and they're only choosing the cold brew because it's so hot outside that they couldn't imagine drinking hot coffee. It could be like, we could just be thinking of random ideas. Okay, so I'm just going to list out a week: Monday, Tuesday, Wednesday, Thursday, Friday. And then the next 5 days would be Saturday, Sunday, Monday, Tuesday, Wednesday. It doesn't say he did it for 5 days of this week, and then they were off for the weekend, and then they did it for 5 days of the next week, Monday through Friday, Monday through Friday. We don't know. So this could be the schedule right here. And maybe just, again, we're being silly. I'm just making some stuff up here. But maybe these Monday through Friday people are super hard workers anyways. These Monday through Friday people. So those people in the box are super hard workers. But maybe these Saturday and Sunday people, it's like their second or third job, and they're exhausted and they're just doing the bare minimum to get by and get that paycheck. So by including them in week 2, it's skewing the results. And it doesn't even matter what coffee you give them. If you have different people in the group, there's other things that are contributing to these results. So as you saw, I kind of just made up some scenarios. It doesn't list any of this temperature or which employees are in the question. I just kind of made them up. But keep that in mind and like make up your own for the third example. See if you can find a third example of a lurking variable. That means something else that's contributing to the results besides explanatory of type of coffee, response variable of production. What other thing besides the explanatory variable, besides the type of coffee, could be contributing? Okay, enough about that plant. Let's look at the last page. Hey, more vocab words. So again, I'm just going to say this because nobody is out there to tell me to stop talking about this. So I'll just keep going. Keep these notes handy, because look at all these words. Look how similar they all are. When you go to do the test, when you go to do the homework, you don't want to memorize this. You want to have this handy. I don't have it memorized. I read it off this list every semester because they're so similar and they're just used this one time. So here's the different scales. A nominal scale is data that is measured, data measured, and it's qualitative and not ordered. So let me just break this up real quick, because we will get qualitative defined here in a minute, but these use words. The scale uses words, and then these bottom two use numbers. So that's the first way we can kind of break these up. But for a nominal scale, it's data that is measured. It's qualitative, meaning it uses words, and it's not ordered. So for example, when you were in kindergarten, perhaps your teacher assigned you to a group based off of colors, and they would say, the purple group goes over here, and the orange group goes over here. What does that mean? Maybe that teacher had a plan, but in the regular world, purple does not mean better than orange. It doesn't mean worse than orange. There's no way to order those. They're just colors. So that's a nominal scale. It's using words that cannot be ordered. However, we do have words that can be ordered. So for example, if I have a survey, right? Like I went to a restaurant and it says, rate the quality of food. And it would say something like satisfactory in the middle. And then it would say like very satisfied. And then it would say not satisfied. You know what I'm talking about? You've seen these a billion times. Like usually there's like 5 words in there. And you kind of rank the different qualities of the restaurant. Well, now we have words that mean something because one of those words is the best. I want you to be very satisfied at my restaurant. I don't want you to choose not satisfied. Not satisfied is bad. Very satisfied is good. So we have words, but we know where, I'm too short for this. I gotta move my camera. We know where we land on in terms of the order of these things. Now, based off what I just said, I had colors in the top and then different words in the bottom. There's actually colors that could fit down here in this. There's specific colors. Oh, I don't know why I just drew that. There's specific colors that fit in the ordinal scale. And I'm just going to tell you them. And as I tell you them, you're going to be able to put them in order in your brain. So if I said gold, silver, and bronze, those are 3 colors that are universally decided as first, second, and third. So that very specific example is an example of colors that can be ordered, but typically colors don't have a better and best and worse. They just are. Now, that doesn't mean you can't have your own opinion. Certainly you could like a color better than another color, but when we're looking at the scale level, we're talking about universally agree. We all agree very satisfied is the best. We all agree that gold is first place. We don't all agree that orange is better than purple. Okay, now on to numbers. So for the interval scale, these have a definite order, and the difference between the scale can be measured. However, it does not have a starting point. And the best example of this is temperature, because we can go on a scale and we can get super hot. And the scientists over here can tell us what super hot means. And then super cold. Hot doesn't mean 100 degrees. Hot doesn't mean 212 degrees Fahrenheit. Hot could keep getting hotter. I say a number and then you just add 1, just keep making the number even hotter, hotter, hotter. Same thing with cold, colder, colder, colder. And so, right, we have numbers. Like I could say that 100 degrees Fahrenheit is hotter than 80 degrees Fahrenheit. I can say 80 is, they're 20 degrees apart. I can do that measurement, but there's no real start and end, and there's like this space in between that we could measure. I could have 80.2 degrees, stuff like that. Another example would be time, just because, in terms of like the timeline of the years, when did Earth begin? Well, before that, the universe, getting into all of these ideas all the way to like, where's the ending of time? That kind of thing, like the timeline in history. Okay, so those are all numbers. A ratio scale level addresses ratios to give you the most information. So if we had a test, for example, and somebody scored a 45 and somebody scored a 90, then we could say that this person, it was twice as good, twice as high, 2 times double the other person's score. That means something. But saying, oh, it's 2 times hotter yesterday than it was, I don't know, in Alaska, that doesn't really, nobody says that, doesn't really mean anything. So we can't really compare that ratio between 2 items. Also, on a test, somebody, I'm not naming names, it's spoiler alert, I'm recording this video the week before school starts, so I don't actually know everybody's name, but somebody will get a 0 on one test somewhere. But I promise nobody will get a -5, right? Like there's a very clear starting point on the test. You cannot score lower than a 0. You cannot score higher than the highest. And in my class, that would be 60 points. You can't score higher than that. So it's not like this forever starting and ending like the temperature or like time. There's a starting and there's an ending. Okay, so here we have a poll is asking people which social media platform they enjoy using more. Twitter, Facebook, Instagram, Snapchat. So those answers are all words, but so that would be the top 2. But, I think I can, yeah, look, I'm going to point to it right there at the top 2. But the words don't mean anything, like the colors. Twitter, it's not like there's a universally accepted social media that's better than everybody else. You like one better. Maybe you don't like any of them. Maybe your friend likes a different one. Maybe your mom likes a different one. I can tell you I like different one than my kids. They're all on Snapchat. I don't have a Snapchat. So my point is, this is an example of nominal because they are words with no meaning. That's not true. Not no meaning, but it's not ordered is what I'm trying to say. All right, number 2, manager gives a test to his new hires. The scores are 50, 80. So we have numerical value for scores out of a possible 100. Which scale level is this? Well, this one's kind of a gimme because I used test as an example, but here, this one's going to be a ratio. This guy scored half on the test. That makes sense because he scored 50 out of 100, that's half. Whereas it doesn't make sense to say, ooh, tomorrow it's really cold outside, temperature is half of the spring temperature. We don't talk like that, doesn't make sense. So if you can say that, then we're typically talking about ratio because that 1/2 is the ratio. Okay, scrolling down, last but not least, more definitions, but one of these we've already talked about, and the other one will make sense because we kind of talked about it without using it. So qualitative, that was listed above. Qualitative means words. There is a typo right here. I just saw it. That should have a D. Words, not works. If I'm smart, I will fix that before I upload it, but if I forget, it's just full transparency. Okay, qualitative is words. Quantitative is numbers. So up above real quick before we go into this example, words. So here we have qualitative. Those top 2 are words. The bottom 2 are numbers. So those are quantitative. Think about like a quantity. What's the, you use the word quantity. That means how many do you have? That's a number. Okay. With quantitative data, we have 2 types. Discrete means counting. Continuous means measuring. So think about your backpack or your book bag or whatever you're carrying all your stuff in. If I said, how many books in your backpack? That is an answer that you would answer by counting. How many books in your backpack? You're going to give a whole number. I have 5 books in my backpack. I have 0 books in my backpack. I have 4 books. You're going to give a number. You're going to count. You're going to give a number. That's discrete. Continuous is the result of measuring. So we would say something like, how heavy is your backpack? Or how much does your backpack weigh? How about that? How much does your backpack weigh? Oh gosh. Spelling is not my strong suit. I don't even know where that T came from. Weigh. That's going to be something that you use a tool to measure it with. So that, like a scale to measure that. And that's going to possibly be a decimal. Your backpack could weigh 10.5 pounds, but you don't have, well, you shouldn't have 10.5 books in your backpack. I suppose if you ripped one in, okay, we're just going to be realistic. Nobody's carrying around half a book. So if you count your books, you're going to get a whole number. But if you weigh your books, you might even get like 10.2 pounds or something like that, depending on how your scale measures things. So continuous is that decimal value, is something that you use a tool to measure it, a ruler, a watch, a scale, something like that. Discrete data is going to be something that you count, and it's going to be a whole number that you're counting. Okay, so John is tallying the number of companies he called each week. So he's like, I'm going to call companies, first call, second call, third call, tallies, right? We're going to do tallies later in chapter 2. 5th call, 6th call, and so forth. He's just making a little hash mark every time he calls. So how many calls did he make? Well, first of all, that answers a number, so it's not qualitative. Second of all, he was counting. So going up to the quantitative definition, we see that it is quantitative discrete. Okay, next, he is getting the mean number of companies, the average, another chapter 2 topic, but you've heard of average before, so you have a general idea of it, even if you don't remember all the details. He's finding the average number of companies his team calls each month for an entire year. So right off the bat, it says number. We know it's a number because it says number. Okay, so it's not qualitative. Now, is it continuous or discrete? Well, mean is a formula. The mean is calculated. Whether you use your pen and your brain or you use your calculator, you're using a tool, you're measuring it. And so this is the quantitative discontinuous because there's a formula, there's a calculator, there's some sort of tool that's being used. You're not counting this. If you could do it on your fingers, you're counting it. If you have to use something to do it, then it is being measured. Okay, that is it for, that's it for chapter 1. Yay! There will be still vocab because we're obviously learning new things throughout the whole year, but we will never have a section as heavy in vocab as chapter 1. So hallelujah. If you have any questions, shoot me an email. Otherwise, see you in the next video. Bye.